הנקודה לשלילי, ועליו אני עושה את בסדר, ואז הגעתי סבבה, הגעתי למקום נכון או לא נכון, ועליו יש לי את הארור, זאת אומרת על actual movement, אין לי איזה סימולציה, אם יש לי או אין לי סימולציה של הפורט, יש לי שני סוגי שגיאות, זו שגיאה של האם הגעתי למקום הנכון ושגיאה של אוסף הפרופריוטציה שלה, אם אני פילינג נכון. שנייה לבדוק.
אני יכולה, אני פשוט חייבת ללכת לאוטו שלוש
בוא נדבר על זה. זה לא אחרי שהוא שאלה. אחרי שהוא שלי. השאלה אם לעשות את זה או לא.
נראה לי שכם כשאלה שבוי, אבל אני לא נשמע לי שזה יחוד. אם אני לא באה לדבר, אני לא כאילו ככה זה בלחץ.
עכשיו לסיפור חדש, או משהו חדש,
לא, כי
אני הבנתי מה אני אבדוק. רגע, אני סגרו אותי. זה שהוא שלי התחיל אופישל עכשיו. לכתוב לך יום. הנטייה שלי כן לעשות את זה, בשביל לא להתחיל להרבה. הנטייה שלי כן, בשביל כן נתתי את זה בשעתי. זה פרש דיל.
אפשר לדבר פעם אחת ב-2:25.
השאלה שלנו לבוא קודם, 2:20 נגיד, זה נראה לי גם אופציה. תבוא ב-2:20. אז לא מתחשבה כבר ב-2:20. טוב, בוא נתחיל. אז בקיצור, זה קשור לשאלה של, כן, הכל פרדיקטיב קודינג, הרחבה למרות איך אתה פרדיקטיב קודינג, שוב קודם דיברנו על סלנות. באיזשהו מקום פרדיקטיב קודינג במוטור זה הכי אידיאלי, זה מה שמושים כל הזמן, זאת אומרת, אתה עושה פרדיקציה למה אתה עושה. בין אם אתה באמת רק פרדיקציה, או באמת אם אתה עושה את זה ומסתכל, זה נשמע פיזי, אבל איך תמיד נשאר בתוך איזה מערך של פרדיקטיב קודינג, חלק אבל השיעור קשן על ה-BBS פייפר הזה, פרדיקטיב קודינג. אבל קבעתי זה הרבה בסוף כל העסק. למדתי הרבה, כי אין מודלים שבאמת יש אימפלמנטציה באופן כל הקונספט באיזושהי אספירציה נורלית.
לא בעבודות על סרבלו. שואלת מספק עבודה להיות דוקטורנטי וקרית אוויר חגי הולך אחורה ונגן הרוח טוב לא נשמע מעניין
הנה השאלה, יש לי שאלה תיאורטית. יש פה predictive coding ל-rivalry. לפי predictive coding, יש דיים אחת שיש לך מכיר ומטפל ודיים אחת שיש לך רחבים ולא מטפל בכלל. מה תראה יותר זמן? מטפל או מה שלא מטפל? This is the question that central אנשים. לדעתי, אולי ההבנתי.
אני מנחש שהמסור הבייג'ים
Okay. There are enough for everybody. There are more than the number of. Okay. נכון. שאל. אוקיי. So good afternoon. I'm very happy, proud to keep my promise to actually do the experiment today. So that's how we'll start the lesson. We'll discuss a bit some other stuff after well, actually, the experiment has some theoretical question at some point. We'll continue discussing predictive coding, and we'll have some comments on the Clark paper, and we'll discuss the comments, etc. But let's start with that. So this is kind of an introduction to what we really want to do, because we were discussing rivalry. Rivalry is when the input to the two eyes is incompatible, in the sense that you can't fuse it into a single coherent picture, and we'll get to it in 2 or 3 slides. But just to give you the context, I mean, the issue, typically, we get a slightly shifted input for the right and left eye, and we manage to integrate, and that's why we see a 3D stereoscopic picture of the world. And this is just an example of how some of these things are produced, to some interesting stuff. Do you see anything which is in 3D? So the idea is that there are 2 pictures superimposed one on top of the other. One is in red, one is in green. And the way we manage to introduce 2 different inputs to the 2 eyes is because through the red, you get the red, through the red, whatever, cellophane, you get the red input. Through the green, you get the green input, and this is why each eye gets only different inputs, because otherwise, if we had these 2 pictures rather than one on top of the other, what we'd have is like fixating or something like this in the middle, and we'd get roughly the same picture to the 2 eyes, so we have to superimpose them and then separate the pictures. So just giving a feeling, and that's I introduce it because this is kind of a part of the history of the study of perception, because people use this kind of picture to show that we do stereopsis in the sense of matching the input to the right eye and the input to the left eye. You all see something? You don't? You should. I think you should. I'm not looking with. Don't you? Okay, at least one person sees something. We can fortify your prediction, and it might help your perception if we improve your prediction. So what do you see? What are you expected to see? Right, but if anybody sees something more specific, a square? When you're looking for a square, do you see it? When your prediction is satisfied, does it help you? You see it. Let's maybe this one. No? This one? Something is outside, something is inside? And how can you change the direction? Put your glasses on the opposite way. In the sense that what the green eye is now red eye and the red eye is now green eye. This is what I mean opposite. Okay. So just for the background, the whole thing in this kind of random dot stereograms were invented by Ulesh in the early 1970s, and the idea was to come up with a demonstration that we can match the input to the two eyes at the level which precedes actual objects. Why? Because when we look at the two eyes together, we don't see an object, but we can yield this perception as a consequence of matching between local items presented separately to the two eyes. So we can match these items, and as a consequence, we get a 3D based, a 3D defined object. But under some circumstances, and this is where we get to our actual lesson, right? These inputs are not compatible. So each picture presented to each of the eyes presents. Okay, so that was exactly the kind of thing we wanted to discuss, right? So the thing is that here in red we have the house, in green we have the person, right? And the story goes, and this is what we're asking ourselves now, that the picture changes between the two eyes in a rivalry manner. So like, and the question is how, okay, who sees a house now? Right. And so switch hands whenever the percept switches. Right, so that would be the next question. To what extent you see a single coherent item, either house or, what do you mean Ratzif?
Face, then it's like half face, half house, and then house. Then house.
Okay, so you don't see them superimposed. You don't see them superimposed, but you see it as pieces, not a coherent house or a coherent person, but you see it kind of part. The question is, does that change? So maybe is the switch, this is what we were discussing, is the switch in a manner that there's an intermediate state where you get part house, part person, and then you get more of a coherent person, and then you get gradually back to the other thing, which was kind of the thing that they were proposing, right? So they said, okay, you start, let's say, I don't know if this was true for everybody, let's say you start with perceiving a face, because faces, we have higher priors for faces, so you tend to perceive the face, but then there is somewhat of a mismatch between the part of the house, which is the eye that gets the house, and is not satisfied by any prediction, and this unsatisfactory or mismatch gradually grows, etc., and this is kind of how you get the dynamics. This was the account of how you get the dynamics of perceptual switch between the two interpretations, right? No. When you are with the glasses or when you're without the glasses?
Now, we can see both the house and, right?
Right. But in a way there's no mismatch.
Yeah, but something it makes
right? Because in this case, yes, I mean, you get something which is in a way coherent with your prediction because you get both. But for a minute, okay? So now, I want to present you with another. Can you look at that? This is another, presumably. Let's see if I have another one. No. Yeah. Can you look at the diamond, and see two pictures? One is to one eye, to the red eye, and one is to the green eye. And now, can you say, okay, note that the red, or what you get in one eye, says yes or no, maybe why. And what you get to the other eye is, I cannot read it, and there's... What is the word? Right, which they produce a non-word, right? And here is the experiment. Now I want us to do an experiment. And the experiment is, what is the proportion of the time that we perceive the actual word, or words, yes or no, versus the proportion of the time that we perceive the non-words, composed of the same... They are what? Okay, so first there is a very strong introspection that you see non-words most of the time, right? I think we have another example. Yes. So maybe introducing a control was a bad thing to do. It's not about not seeing or seeing, but the proportion of the time. Did you have a... You saw the word? Okay, let's do this. What do you see more? So here comes the question. Following the idea, the concept of predictive coding, what do you expect to see more, a larger proportion of the time? Are you expected to see more, a larger portion of the time, the surprising input? So think of it for 2 minutes and then I'll ask you to... Okay. So here's the question. And yeah, this was the experiment. So here's the question. Given predictive coding rationale, what do you expect to see a larger portion of the time? The predicted hypothesis, which of course is the one that I mean, here it's very clear that you're more likely, or your prior is higher for existing words than for non-words, right? Let's just a second. Let's assume for a minute that in terms of actual, bottom-up discrepancy between your prediction and the actual input, they're the same. Okay. So what would you expect to see a larger portion of the time? So whoever wants to say something, yes. Okay.
Probably the prediction because this is how we minimize prediction error.
Anybody?
Wants to learn more about the surprising thing.
This is a good idea, but is it in line with prediction error conceptualization? So let's go back. So let's go back to how to the account in the paper that I presented last week about what is it that leads to the change of the percept, right? The input doesn't change, right? But the percept switches. So it was switched favoring. If everything else is the same, let's assume for a minute everything else is the same, then you would prefer, this is my understanding, to perceive the thing that goes along with your prediction. And it makes sense. From a statistical point of view, it makes sense. Right? Because if everything else is the same, so the actual evidence for either, the actual bottom-up evidence for either alternative is the same, but you have a larger prior for one. Statistically speaking, it makes sense to perceive that one. But I totally agree with your intuition that if you want to learn novel things, you will learn less in this way, right? Because you're not about to change your model so as to satisfy the alternative, the surprising alternative.
So it might make more sense to perceive the more familiar one at the first instant, but once you see the unfamiliar one and you know that it's there, the non-words, you know that it's there, so then they're equal probability, because you know that they're both on the screen.
So this adds an interesting question as to how quick you are in adapting your prediction, right? So to what extent, right? Because there is an alternative account, and this alternative account maybe should be upgraded in terms of the prior, but the way I see it, it's an important thing. I don't, at least with the conceptualization that was presented there, there's no such place. So in a way, at least my interpretation is that if you want it to work, you need to add something else, and this gets to, which we'll get to, the walking in the dark room. Walking in dark room. This is now the time. This is now a good time for what do you expect to happen in a dark room commentary. Are you going to present? Yes. Will you present now? Because the question, the way I see it, and you will say something about it, is that there's no additional input for our interest in learning new stuff, our basic interest in learning new stuff, right? If we just want to decrease the distance between our prediction and the world, there's some very easy way to do it, and it doesn't mean that it cannot be amended, but it doesn't introduce the incentive to learn new stuff when you can avoid it in a way and be happy, potentially. So, the first commentary, אני חושבת, כן. כן, זה אמור לעבוד מפה. So the first, I want to introduce, to mix my own commentaries, and אולי ניתן לך, אני אכתוב את הראש.
כן, זה הכרחי. טוב. פה? או, אוקיי, זה בסדר? כן, טוב. So the commentary I'm going to present is maximal mutual information, not minimal entropy, for escaping the dark room. So I decided, I figured this is going to be the first commentary presented, so I decided to do a short recap about what the modeling actually is. So there are several levels of computation in the brain, so I'm going to stay abstract here. I don't want to get into the anatomy. So I'm just going to say there are several levels of computation, several areas that each compute like different low-level or high-level information. So the sensory input is arriving to the low level. I'm going to start with the high level actually. So the high level is trying to predict on the high level what is going to be the sensory information. Yeah, and then this prediction, you can see it here in the prediction, the high level computes, and then this prediction propagates back to some medium level area or less high level area, which computes also its own prediction that is based by the prediction, the top down prediction and the local prediction that it computes by its own. And then this prediction is sent to even more low level area, which also computes its own prediction based on the modulation from the higher area. And it receives sensory input, and now it can compute the difference between the prediction and the sensory input, and this would be a prediction error. So the prediction error propagates forward back to the medium level, and its own prediction error computed is propagated by its own to a high level. And to make this more intuitive, so I wanted to give like this very intuitive example. So if I'm going to a concert, so it might be either a blues or a rock concert, so I figure because of things I've heard, it's going to be a blues concert. So then I predict that the sensory information that I'm going to receive is some, blues music, right? So this prediction modulates the prediction of the more lower level area, so it might compute like melodies or something like that. So if I think that I'm going to be in a blues concert, then the melody is probably going to be blues melodies, and this propagates back to the tone level and predicts what kind of tones should appear after what kind of tones. So after tone A, if it's blues music, it'd probably be tone B, not tone C. And then finally I arrive to the concert, and it's more rocky than I thought. So the tones that are appearing after, other tones are not as I expected. So there's some error which propagates back, so the melodies are not exactly blues melodies, they are more rock melodies, and it is also a prediction error, and this is propagates back, and this is not exactly a blues concert, and this is the main idea as much as I figured. So this kind of model must have another thing that is added by Clark is the motor control. So eventually, our purpose is to minimize the prediction error, and it is also done by a perception action loop. So by this motor control, I actually affect the sensory input that arrives. I actually can affect the world, and thus affecting the sensory input that arrives back to me. So this whole loop, its whole purpose is minimizing the prediction error. So I can minimize it by changing the synapses or whatever. So my prediction will match better the sensory world, and I can also change the sensory world by my motor control to better match my predictions. So as it's presented by Clark, this entire loop is here to actually minimize the prediction error, and computationally you can make an analogy between the prediction error to the free energy, and eventually you want to minimize the free energy, and hence minimize the entropy, which will be some sort of measure of energy over longer periods of time. So if my prediction is perfect, so there will be a very certain state that my brain would be in, and then there will be no entropy because it will be very deterministic. I know exactly what will be the next state of my brain. But if I'm not predicting perfectly, then there's going to be variation between the sensory input and my prediction, and it's going to be less certain what would be the next state of my brain because my prediction is not perfect. So it's actually, the thing here is to minimize entropy. So now we can think about what would be the stable state of such systems. Such system that actually wants to minimize prediction errors. In its stable state, you will predict perfectly what the sensory input is going to be. And eventually there will be no prediction error propagating back because I predict what I'm going to see or what I'm going to perceive perfectly. So when you think that if a system wants to get to this stable state, that it predicts perfectly what the input is going to get, so the very good strategy for the animal or whatever this is, the brain is, the very good strategy would be to just go into some dark room with no sensory input and just stay there, because it's very easy to predict no sensory input, right? Because if I'm in a dark room, I get no input, I predict I get no input, my prediction is perfect, there's no prediction error, and this would be the best thing the animal can do. So how do we solve this kind of thing? So Clark suggests a solution to this problem. So more or less what he says that I predict the world to be unpredictable. I predict my behavior to be unpredictable, and therefore I should do unpredictable thing or more complex behavior because this is what I predict. What? It's weird. It's kind of tautological, right? It's kind of circular. He gets further specific, but he's saying that we have priors actually. So my prior, like this is a prior that I can avoid, my prior thought about the world is that my behaviors are going to be complex and not steady, and I can control my prior. So in order for me to predict perfectly, I must conform to my prior and do some unpredictable things or some complex behaviors, which is, I don't know, it's kind of weird explanation, but it makes sort of kind of sense because we are all different and we all have different behaviors, and it kind of makes sense to think that we have different priors and different balances between our exploration and exploitation. So eventually the comment would be the first, the Clark's explanation sounds tautological because he said we act so that we can predict the outcome of our actions. We predict that our actions will be complex and interesting, and therefore we act in complex and interesting way. It's like saying, I predict that I will clap in 1 second, and then clapping, and now I'm psychic, right? Because I predicted it. But it's kind of circular. So they have a little problem with this explanation, but the fact that he introduced priors, actually, it removes this circularity, as far as I understood it, but it weakens the ability of the minimize the prediction error, the minimum prediction error to explain complex behavior. because everything now could explain by I have very complex priors, which could be the only reason for why I behave in different ways, and then I can't really use the minimum prediction error to explain behaviors, because the priors have such a great impact on behavior. So the thing that is suggested in this comment is instead of minimizing entropy, maximizing mutual information. So first of all, this is not a new concept. So there's a lot of theories that say that maximizing mutual information would be beneficial to a behaving organism. One of these theories mentioned in the comment is by our Untitled Chapter. So this idea I actually learned about in the information processing course. So maximum mutual information is between the sensory input and my prediction. So the greater mutual information between my prediction and the sensory input, the better my prediction is, right? So if I talk about entropy, so entropy is the informational cost of a bad internal model, right? So if I talk about mutual information, so this is the informational gain of a good internal model. And the thing is, so it sounds like a technicality, right? It sounds like a mathematical technicality. Okay, so I maximize this, I minimize that, eventually it does the same. It minimizes prediction error, but the actual difference is by the actions, right? So we saw the perception action loop, and the actions is where the difference between the mutual information maximization and the entropy minimization lies. So I didn't want to put any mathematical equations to demonstrate it because this would be tedious, so I decided to use a graph that is used by Tali to explain mutual information. So if I thinking about my prediction of the sensory input and the sensory input itself, so it has some overlap. So the overlap between my prediction and the sensory input would be the mutual information, and the areas that are not overlapping between the prediction and sensory input would be the entropy, would be the uncertainty in my prediction. So everything I predicted that didn't happen would contribute to uncertainty, to entropy, and everything that happened and I didn't predict it would also contribute to it. So if I'm going to a dark room, then I actually take the blue circle, the sensory input, and I make it very, very small because there isn't any sensory input, and my prediction will also be very small because I predict there won't be any sensory input, and then I actually minimize the entropy, right? Because if these circles are very, very small, so the entropy area will be very, very small, but at the same time, I minimize the mutual information too. So if I try to maximize the mutual information, so I don't want to make the circles very, very small, I want to make the overlap big. So I will do it by balancing the sizes of the circles themselves, my exploration of the world, my complex behavior, and still making good predictions by making these circles overlap. And this way, the dark room wouldn't be, I still minimize prediction error, but I still balance it with complex behavior, and the dark room wouldn't be a very good solution. So this is what they propose. So Clark's response to this, so he says the alternative is merely cosmetic change. So he said it's just a technicality, the mutual information, the entropy. I don't think it's a technicality, but I don't think it's a big flaw in. I don't think it's a big flaw in the model, in Clark's model. And another thing he mentioned is the musical room. Say, so okay, so if I want complex behaviors and I want a variation in my sensory data and I have a rich sensory input, so I can go to this musical room where there's a lot of sensory information. Doesn't have to be auditory, but a lot of sensory information in the room, but it's a room, it's predictable. I stay in this room, I can learn the way the sensory information arises, and then I can predict the sensory information in this room. So he says, so now we created a new problem. So now it's not a dark room that the animal wants to go to, it's a musical room where there's a lot of sensory input that it can predict. And to my opinion, this is life, right? Musical room, because we try to find the environment that we can predict, but it's still complex enough for for us to feel good in some some beneficial way. I think this also describes animals that have their own territory and can they prefer to have their own territory when they can learn in their environment and still have a variation of sensory input. So Clark presents it as a new problem, but I don't think it's a new problem. I think it's actually a very good description of what life actually is.
What is the problem there?
So it says, so now you replace the problem of the dark room, which is like a very predictable environment with no sensory input, you replace it with the musical room, which would be a very predictable environment with sensory input. So Clark called it a new problem. It just replaced one problem with another. To my opinion, it's not a problem. This is actually what life is. This is, to my feeling, what actually humans and maybe probably animals aspire to a predictable environment that you're not surprised too often, but it's still full of sensory input and not just this dark environment. I think that's it for the first comment. So, questions about that?
So what does maximizing mutual information predict for the occurring rivalry words versus non-words?
So I didn't think of that yet until now.
No, I think the reason I presented it just before the dark room was exactly for this reason, right? For the same, generally speaking, it's the same kind of difficulty, where the question is that it lacks in a way the incentive, right? The formal incentive of the performer, human, whatever, animal performance, to increase its overall predictability of the more complex world, right? Because the problem is that when you have something which is highly predictable, it has the same, right? It predicts that by counting alternatives, that it does predict that we'll see the more the option with the higher price. Or you can decrease your unpredictability by just closing your eyes, but then you lack something that this is not how we behave. And by the way, just remember that I forgot to tell you that this is an actual experiment with the words and non-words, and that was done by Charles Hofstein. I want to just to show the results. Well, it doesn't matter. The results are really very much like you got informally, that overall people experience a larger portion of the time the non-words than the words, and it's the non-predictable that we kind of cling on to as kind of we tend to. So there's some incentive in learning, and there's an issue because, as I said, from a statistical perspective, you do want to have the better prediction, the better predicted input as your perception, but it doesn't get you learning, right? Because you'll not get the chance to modify your internal representation so as to accommodate unpredicted or less predicted or alternatives. But on the other hand, I didn't think about it either until I asked you, but I think I like the mutual. I mean, it doesn't give a specific implementation, right? Conceptually speaking, the mutual.
In the next comment.
Right?
In the next comment, it would be more implemented.
You tell us how to do it. Okay.
No, not exactly, but.
Intuitively, I think that it does. It should increase mutual information in this case.
So I think like perceiving the non-words too would be like exiting the dark room. Instead of ignoring the world so I can predict it better, I just go and explore the other sensory input in order to maximize my mutual information. Because if I see the non-words too and I'm able to predict them, then I have more mutual information with non-words now. So.
Yes, that's how my intuition works.
Yeah.
So in a sense, one option is that there's some explicit, as you suggest, some priors introduced into the system that are explicitly interested in exploration or something like this. Or the alternative is to put some benefit on actual acquisition of new information, right? Because if there's no information and so you're fully predictive, but you're getting none from it.
Yeah,
so,
no mutual
so
information.
another way which I think works for that in principle.
Yeah.
I think you can go for a second comment.
Okay. It's like pretty much related. You're gonna see why. So the second comment is more of a balagan because it's not really clear what's the message. It seems like this guy just wanted to talk, but he says he says because I just chose it yesterday and all the best ones were chosen. But that's some interesting things he says. So so I'm gonna make it as interesting as I can. So first of all, there's a mention of the curse of dimensionality. So basically, what's going on in this comment? So there's a comparison of the model Clark described and another model called the Infomax. that I think you learn about it in neural networks B, right? About Infomax. So there's a comparison between both of these models and the problems they solve and the problems that Infomax the problems that Infomax solves and Clark's model doesn't solve, and so on. But it's kind of a balagan. So we'll just go over it. So first of all, there's a mention of the curse of dimensionality. So this is a computer science term. And it is obviously relevant to the brain because sensory information to the brain is of high dimension. So obvious examples would be photoreceptors in the retina. So we have about 1 million photoreceptors in the retina. So there's about 1 million degrees. Oh, 1 million ganglion cells, right. Okay, right. So we have N photoreceptors in the retina. Each one we can say have a D discrete states to make it simple. So we have D to the N possible inputs to the retina. This means that the number of different stimuli grows exponentially with the dimension, because D would be the discrete state of one receptor and N would be the number of receptors, so it goes exponentially with the number of with the dimension. It's the same with the cochlea, with the hair cells and the mechanoreceptors, and everything is the same. The number of receptors would be the dimension, and the more there is, the more dissimilar the inputs one another. So novel events are highly dissimilar to previous one. So thus precluding example-based learning. So if I see one cat in the upper right corner of my visual field in a red room, and it's far away and it's black, and then I see a ginger cat in the lower left corner of my input and it's a green room. So both of these images look completely different from one another. And if I just take the vector of the pixels, I can't really deduce that they're both eventually pictures of cats. Okay, because they're so dissimilar from one another. So this is the curse of dimensionality eventually. So this is a major problem that must be solved by the brain, and as we know, it is solved because we are able to perceive the world. So the solutions are, first of all, large databases must be divided into small subsets. This is also the computer science solution, and we know the brain does that, right? Because we have the receptive field, that each receptive field is in charge of like a different part of the retinotopic organization, and we have orientation versus color neurons in V1, that each one takes a different portion of the information, and we have the dorsal and ventral stream in the visual cortex. There's some information about what are the objects goes in one place and where the objects goes to another place, and it's crucial that every one of these regions gets only the information relevant to its use, because I can't be distracted when I'm thinking where is the stimulus. I can't be distracted by what it is. I can have information that is not relevant for use, because then I go back to the curse of dimensionality and I can solve the problem of where the tiger that is after me is. And the same for the other direction. This must be a context dependency. So this is, I can go back to the concert example. So if I'm in a blues concert, I expect blues melodies, and therefore my prediction error will be smaller because my prediction is dependent on the context. So there must be context dependency, and so local processors must be guided by the broader context and must be coordinated. So if my ears expect a blues concert, my eyes should expect a blues concert, otherwise there'll be a discrepancy between the information and wouldn't be effective. So all of these solutions that exist in computer science to the curse of dimensionality, also in the brain. The problems that are introduced now, that the predictive coding models proposes transmission of information through a hierarchy, but not how the information is selected. Okay, so there's no, Clark didn't mention everything, how exactly the information is transmitted from lower areas to higher areas in a way that is beneficial for behavior, only that this is the way it is. And we know it's the way it is, right? But we don't know how it's performed. And Bayesian inference models describe how several streams of information can be combined, but not how the relevant information is selected. So again, this is like a mechanistic explanation that these theories lack. So local selectivity and contextual disambiguation and coordinating interaction, which are all the things I just mentioned, are necessary for cognitive systems, but can't be explained by predictive coding or based on inference. So the advantages that do exist in the model that it describes prediction as the prediction error as free energy, and that has to be minimized selectively. And this way, by context, I could the context from the higher area could tell the lower areas which prediction errors are more important and which ones should propagate back. Okay, so if I'm thinking I'm in a blues concert, so I'll be focusing about the melodies of the concert, so because this is what more beneficial for my current prediction, and other things might be ignored, like who are the people in there. This is not important for me because it is not relevant to my current prediction. So this is an advantage in Clark's model, and this is what's called gain control or attention. So there's a connection that Clark presents between this context relation to attention, that I can select which one of the prediction errors are more important right now, and which one should mold my synapses and the correction of prediction. But this is also done by Infomax. Infomax is, again, the maximizing of mutual information. This is a theory relevant for neural networks, but Infomax also describes the mechanism, describe how this might be performed by neurons, and we also already saw that the maximization of mutual information is a solution for the dark room. So another thing that none of these models actually answer is what about the diversity of brain and cognition? So we say, okay, these brains, they all have this one principle. We want to maximize mutual information, and this is like a single principle. So what causes the diversity among brains? What actually make different organisms or between species and within species act differently from one another? So Infomax hypothesized that a local building block from which endlessly many architectures could be built, but there's really no explanation of how this is used by brains actually, and why brains are so different from one another. So to summarize, there are similarities between hierarchical processing, HPC, hierarchical, predictive coding, okay, yeah, and Infomax, and highlights their benefits. So Clark, in his response, says that the models complement one another, but Infomax gives the more mechanistic details of how this is performed. But also the universality of these models leave us in explaining what is this diversity in brains. And again, maybe we should go and listen to this guy some more about his theory, because it makes much more sense now that it's not just math. And I think that's it. Yeah.
Just one question before the break. Okay, you have one.
So, to me, both of these responses seem to deal with the question of motivation. In other words, why are we choosing to be in this environment instead of another environment? What are we choosing to maximize? I mean, to me, this is all very strange. It's very strange to come at these kinds of questions from an information theoretic perspective, because rule number one of life is that we're sexually reproducing biological organisms. Our goal is not to maximize sensory information. Our goal is the 4S. We have to reproduce. We have to eat. We have to do the things that biological organisms do. So this entire direction is strange to me. In other words, I understand these kinds of models in terms when it comes to perception, but in terms of motivation, there are broader things that we should be thinking about.
That's right. There's another comment that I initially chose to present, and then it's about reproduction, but I don't think it's a good comment, because there's no relation to this model. They just talk about their model, and then they say that the fact that we do Bayesian calculations it sits well with their model, but they don't explain why or their model. But I try to think about it a little bit. So as far as I see it, our need to eat and to reproduce is not a computation done by our conscious, by this model anyway. This is a sort of an input, like a sensory input. The fact that I need to reproduce and the fact that I need to eat is an input to this model, and now I have to predict it, right? I can control it in some way, but not much more than I can control my sensory environment. So if those needs are inputs, so I have to predict them and I have to conform to them. And I think the need, the fear from being eaten or the need to reproduce isn't the computation done by our conscious, our conscious brain. I don't want to say cortex, but those needs are a sort of input that we have to predict. These are given, like our sensory world.
I would say it's the opposite.
The opposite?
I think, in other words, in order to get a particular goal, that I need to eat, so therefore I have to get a job so that I can make money. Those are all very high-level conscious things. I think that those are the things that we spend cognitive energy thinking about. This kind of leads to perceptual kind of stuff that you want to know about.
But it's not that I'm thinking I need to eat. I am hungry. It's a given, right? It's given, like there's chairs in front of me. It's given. I can control that. I can move them around a little bit, but the chairs in front of me, so I'm hungry. I can control that, right? So I have to predict it. I have to predict me being hungry, and I have to predict me eating, because this is a behavior that I can't control. And the behavior of eating and reproducing, as far as I see, is automatic. It's not voluntary. So I see it as an input, and not as a decision, not as a computation. But there's no explanation in the text. This is because it bothered me the same as it bothered you, so I thought about it a little bit. So this is the best explanation I could come with yesterday. This isn't written anywhere, but this is my opinion. So maybe Merav has something, I don't know, more grounded to say about it.
I think the open question here is whether such levels of conceptualization should really include goals, basic incentives. They don't, right? So the question is, should they be, in a way, less pretentious and admit that they don't, and this is beyond, so as you're saying, there are some inputs that, it's not this concept doesn't have all the inputs yet, and it's a starting point. But on the other hand, and this is why I thought this experiment is interesting, because it's not obvious to me that even if we sort of take all these sort of big motivations of ours as something that's not into the model yet, it can account for our behavior. For instance, like simple conceptual, why don't we close our eyes and things like this, even beyond the big goals of high-level intentions. I'm not sure it is sufficient to account for it. Even how we balance our perceptions, because for me it's an open question, which is not addressed here, that we have. It is consistent with the mutual information. So we want to know more about the environment, and we have incentives to learn more about the environment that are not embedded in this conceptualization and are relevant, even for percepts, which are not there. And I don't think, so mutual information could be relevant, but then it leaves the question to other issues. What is information? Not everything is important. It's the information that is relevant for better reproduction, for better rest, for attaining our goals, because it leaves the way, okay, so we need to acquire information, but does it tell you what is there's lots of stuff out there which is really not interesting for us, and we're not going through. To what extent we can, based on this general conceptualization, mutual information predicts, forget the mechanism, but just what are we going to go for now? You have to have external information for information, goals, etc. So I don't think any of these ideas addresses these questions here. Let's take a break.
Okay.
We have other comments, 2 other comments.
אגב, מה שאמרת בסוף, אני מאוד מסכים. כאילו, מה זה מסכים? נראה לי הגיוני.
מה שזה אינפוט?
שהריוורד של אינפוט.
באופן כללי, כמה פעמים אמרו שם שה-reward system זה משהו שצריך להושיב אותו עם המודל הזה, הוא לא יושב עדיין טוב עם המודל הזה. כן.
אני חושב שאפשר להוסיף. רגע, זה... אני יכול כאן?
שכנעו אותי בסוף. מי יראה את זה? אתם מקסימום.
רגע, אני רוצה את זה.
דיברת על ה-gain control,
כן.
שהוא דיבר על זה. הקטע הוא שכל המטרות האלה שפה נדבר עליהן.
מה, להתרבות ולאכול
יש לך בעצם את המטרות האלה שנותנות, עושות gain control לפי דברים של המסה, משהו טוב, או אבולוציונית למסה.
אבל אם אני רוצה עכשיו להגיד במילה אחת שמה שהמוח עושה זה maximizing או minimizing prediction error, לא משנה mutual information, סבבה, זה...
שיט, מי שצריך to sign in?
לא, צריכה sign in פשוט.
איך עושים את זה? איזה עבר זה?
זה לא זה?
זה זה.
מה?
אני התכוונתי את זה כאילו מטרות.
מה זה המטרות האלה? המטרה שלי?
כאילו זה מנגנון שנועד כדי לשרת את ה... נגיד, אתה חוקר, למה? כי אתה רוצה למצוא.
אז מה המנגנון של מטרות אז? מבינה, מה שמנסים להגיד זה שהמנגנון שיש זה to minimize prediction error, זה המנגנון שיש. כל ההתנהגות שלנו היא סף מאוד גבוה של זה. זה מה שמנסים להגיד, כי אחרת אם את אומרת טוב ויש גם מטרות, אז טוב, אז צריך להגיד מה המטרות האלה ומה המנגנון שלהם.
הם אלה שיצרו את המנגנון הזה, כאילו נגיד, אני צריכה לחקור את הסביבה, למה שאני אחקור את הסביבה? כי אני רוצה למצוא אוכל ואני רוצה למצוא בני זוג פוטנציאלי, או למה אני רוצה למפות את הסביבה הקרובה, כי אני רוצה מקום בטוח שאני לא...
מה ממפה רצון? בואי נגיד שסבבה, אני לא
אני
יודע מה מייצג רצון, אבל מה ממפה רצון להתנהגות?
מה זה הפרדיקשן? פרדיקשן זה מודל מסוים שיש לך בראש, נכון?
פרדיקשן זה שאני מקבל סנסורי דאטה, ומבחינתי אני חושב שכשחושבים על סנסורי דאטה, כאב בעצם זה סנסורי דאטה? וזה בפנים, נכון? אז בפחד זה סנסורי דאטה?
כן, אבל זה בסוף זה משהו שיותר...
לא, פחד זה לא... למה זה לא סנסורי דאטה? אין, נוצר פחד עכשיו, אין לך מה לעשות עם זה, זהו, נוצר פחד עכשיו. ומה זה שונה מכאב בטן?
לא, זה תובל סנסורי.
אבל אני לא בחרתי לעשות את זה.
נכון, אבל זה לא סנסורי.
למרות שזה נורא אבסטרקטי לזה.
זה תובל סנסורי.
למה כאב בטן? שזה גם בתוך הגוף שלי.
אתה לא נמצא בתוך, כאילו, חדר חשוב וזה, אז פתאום מתחיל לפחד. כלומר, כן, כי יש תהליכים אחרים.
סבבה, אבל זה תגובה לסנסורי אינפוט. גם אם עף עליי כדור, זה תגובה לזה שמישהו זרק את הכדור, אז גם הסנסורי אינפוט הוא תגובה לסנסורי אינפוט. אין בעיה לעשות את ההיררכיה הזאת בעולם החיצוני.
לא, אבל אם זה תוצר של פעילות המוח שלך, אתה לא יכול להגדיר את זה סנסורי אינפוט, זה לא.
אוקיי,
אבל זה לא סנסורי בעיה ראשונה.
למה? זה נובע ממשהו שקרה בחוץ.
זה עקיף.
זה הלך לרצפטורים שלי.
לא, זה קרה למשהו שקרה בחוץ, הלך לרצפטורים שלך, ואז הגבת בצורה שיצרה פחד.
אז מה שאני מנסה לגזול פה...
שכל המנגנון של האינפורמט וסנסורי אינפוט, בגלל שזה נוצר בתוך המוח ובתגובה לדברים חיצוניים.
אז כאילו מה שכל זה גרם לי לחשוב זה שהמודל הזה לא נכון לכל המוח, וחלק מהמוח הוא סנסורי ריספטור בדיוק כמו פוטוריספטור ומקנו ריספטור, וכשאני אומר חלק מהמוח אני מתכוון למקומות שמתחילים פחד, מגדלה, כל מיני כאלה, אין, הוא עושה משהו צריך, הוא מקבל מידע.
זה לא סנסורי, אבל
זה לא סנסורי, אבל
זה מושפע מהסנסורי.
זה עדיין בגדל האינפוט.
ואז זה אינפוט,
כן.
כאילו סנסורי למקומות אחרים.
אז כדי להשאיר את המודל הזה בגדר, כל המטרה שלו זה למנם prediction error, אז מבחינתי כל מיני דברים כמו פחד וכל מיני אינפוטים מהמגדלה והערך הם אינפוט.
You need to control them.
כן, זה משהו שאני צריך לפרט, זה given, כאילו. אני לא שולט בזה, זה משהו שהוא קורה אוטומטית כמו כאב בטן, שאני יודע שזה סנסור אינפוט, אבל זה קורה בתוך הגוף שלי, אז גם זה עם עשבים, אבל גם המקן הרצפטור, הקימוריספטור בבטן הם עשבים בסוף, נכון?
הקטע הוא שאיך אתה בונה מכניזם שגורם לך שכשאיזשהו נוירון יורד, אז אתה צריך לברוח. איך אתה עושה את זה?
אני חושב שפליינג behavior זה אינפוט.
רע או טוב?
ה-behavior הזה הוא אינפוט.
לא, אבל אני מדבר על המנגנון הזה.
הקוויש אבולוציונית זה מפחיד.
סקדות בעיניים.
למה כאב זה רע?
סקדות בעיניים זה פעולה שאני מחשב כדי לעשות מינימום ל-mutual information? לא, נכון? אני עושה התנהגות...
כאילו, אני לא יודע, כן. סקדות בעיניים אני חושב שזה לא אינפוט. סקדות בעיניים אתה לא נתון.
אבל זה לא
אתה מחליט לאן לעשות.
לא, אתה לומד.
סקדות זה כן נתוני.
אתה לומד.
אתה מחליט לאן להגיע.
אז זהו, שהדברים שהם בגזע המוח אני לא יודע אם הם נשלטים בכלל. התנהגות בריחה, אני לא יודע אם זה משהו שאני שולט בו, אם עכשיו תבוא מפלצת, אני לא אומר, יש מפלצת, אני אברח.
אבל איך אתה יודע מפלצת בכלל?
אבל זה אימפול שאני מקבל, הגוף שלי מבחינתי הוא חלק מהעולם החיצוני, ועכשיו הוא בורח.
אני לא חושבת שאם אתה לומד ואתה יודע להשתיק,
נכון, זה מה שאני חושב, שהדבר הזה הוא לא רלוונטי לאיך המוח פועל, הוא רלוונטי לאיך לא יודע אם זה הקורטקס, כן מושג מה עושה מה.
שתי מערכות, אחת נשלטת ואחת אבולוציונית קדומה ששולטת.
בדיוק. וכל הדברים האלה שהם אוטומטית, כמו רעב, כמו פחד, וכולל הפעילות שאני אוכל.
אבל יש לך ביניהם, אתה משפיע אחת על השנייה. אתה לא יכול להפריד ביניהם.
יש אינטראקציות ביניהם. יש אינטראקציות גם בין המוח לעולם החיצוני, ואנחנו לא מפרידים ביניהם, זה סלור.
אבל איך אני רוצה תשובה לזה? איך אני...
אבל יש דברים שמפחידו אותי בהתחלה, ואתה אומרת לא לספר למשל.
אין לנו בעיה, נכון? ראינו את המוטור קונטרול, סגירה של הלופ, שאני יכול להשפיע על העולם החיצוני, אז אני יכול להשפיע גם על מה מפחיד אותי, כמו שאני יכול להזיז את הכיסאות האלה, ועכשיו אני רואה כיסאות מפחידים.
אבל מה שאמרת שהתגובת בריחה, זה נגיד גזע המוח,
אז 3 פעמים ככה?
ואני שולט בגזע המוח, נכון? אני שולט עליו, אבל אני לא שולט עליו כמו שהקורס מדבר עם עצמו, אני שולט עליו כמו שאני יכול לשלוט על העולם החיצוני. ככה אני רואה. כל זה מה שחשבתי עליו אתמול, בגלל שחפרתי את הדבר הזה. קראתי את רוב הקומץ,
זה משהו אתה נהיה מומחה במשהו, אתה תשים לב מסוימים,
ככה אני רואה.
זה לא משהו שהוא מולד, הדבר הזה, זה משהו שהוא נלמד. וזה אולי משהו ש...
לא, זה שאני לא
אתה מסתכל לסקדות,
זה לא...
זה משהו שהוא נלמד.
אתה מחליט לאן להסתכל.
אתה לא מחליט, זה קורה לבד.
מיקרו-סקדות. מיקרו-סקדות אנחנו לא
זה שאתה בוחר להסתכל על העיניים.
העיניים כל הזמן זזות ככה. גם כשאתה ממוקד על משהו, כל הזמן זזות ככה.
זה משהו אחר, זה חלק מהמנגנון הפנימי שגורם לזה שאתה יותר אינפורמציה.
זה שזה פעולה מוטורית, ולברוח לחיה או לאכול כשאני מאוד רעב, זה אותו הדבר מבחינתי. שזה פעולות מוטוריות שקורות אוטומטיות בשואה, הם אכלו עצמם כאילו...
זה מעט מאוד קניבליזמים בכלל,
כן.
זה לא קשה.
העניין של פעילות אוטומטית, בסופו של דבר אתה רעב מספיק, אתה תאכל ואתה לא תשלוט בזה ואתה תאכל. הגוף שלך יעשה את זה, ואתה יודע, גם הליכה, אתה לא מוכן טוב, אתה לא עושה את זה, זה משהו שקורה, נכון? אתה שולח את האינפוט של ללכת, אני שולח את האוטפוט של ללכת, והגוף שלי שהוא חלק מהעולם החיצוני, שהצבתי עכשיו, הוא עושה המנגנון של הליכה בספיינל קורס.
לא הבנתי למה זה
אחר כך מה שאתה עושה את זה הרבה פעמים, יש לך גם...
יש דברים אוטומטיים ויש דברים שהם כאילו לא אוטומטיים.
אבל האם אני נלמד את
זה?
מולד.
לא הלאכול שלנו, אבל הלאכול של חיות, ולברוח וכאלה, הם כאילו אינפוט. שאני יכול לשלוט בו, אני יכול לשלוט בכמה אני אוכל.
יכול אינפוט. גם כשאתה חושב עכשיו, אוקיי, אני רוצה מחר
יש שם סוף דרגות חופש.
כי יש שם לפני, אז אתה חושב, זה ממש מורכב,
אבל זאת החלטה כזאת, כן החלטה שהייתי אומר, בעד לעשות מינימום לפרדיקשן. כי אני נורוסיינטיסט, ואני לא רוצה להיות מופתע, אז אני הולך לעשות שנורוסיינטיסט.
לא תחמים בגלל העניין.
יכולת החיזוי שלי לגבי נורוסיינטיסט פוחתת, נכון?
אתה לא מסכים?
למה מוזיקה? מה אומר לך למוזיקה?
יש לך מוזיקה שהיא פשוטה, שהיא פרדיקטית, ויש אנשים שרוצים את זה.
את אומרת שאני לא בוחר.
בוחרים מוזיקה שתמיד פרדיקטיבל עם טיפה קצת שינוי. ויש אנשים שיש להם יותר אקספלורטורי, ואז הם לוקחים מוזיקה ממש לא פרדיקטיב, ולומדים אותה, ואז מרגישים נוח בשיר שהוא לא פרדיקטיבל, ואז יש להם פרדיקטיב שלו, ואז הם מחפשים שיר אחר שפחות פרדיקטיב.
למה מה שאמרת זה רלוונטי? למה מוזיקה ולא...
סבבה, אני מדבר על מנגנון שעושה את זה.
למה לא... רצון לעשות באקדמיה.
אני לא אומר שזה פחות להתרבות, בא לי, זה ממש לא יותר טוב, זה קל. זה פריימורק שקל לעבוד.
ואז האינפוט, התחושת פחד והפעילות של הבריחה, אלה אינפוטים שזה מקבל. הם לא דברים שזה בחר על זה לא אכניס את הבחירה.
כן, זה חשוב.
סבבה, נכון, אני לא אכניס את הבחירה שלי, כי גם זה פילוסופי וגם שזה לא ישאר. פשוט יש את המנגנון שעושה את זה, ויש את המנגנון שעושה דברים הרבה יותר בסיסיים ואוטומטיים, ואת כל הדברים שצריך לציין,
אולי אני הולך לעבוד על עוד
המנגנון הנמוך יותר ולא
לא בשביל מוזיקה.
אתה לא יודע מה נייצ'ר אוהב.
מה הנייצ'ר? אני רוצה לבנות מחשב שעובד, שעושה עבודה נהדרת.
לא יודע, אני יכול להגיד.
זה אני מסכים מאוד.
אתה יכול, יש לנו גם מודלים.
לא מעניין אותי לעשות את
כל
המוזיקה.
אחד יש מודל אחר בראש. אתה יכול
זה גם משתוקן, זה משתדל להיות כמה יותר אבסטרקט כמו שהייתי פעם.
בסדר, תקבל.
מעולה.
אבל...
מודלים יש כמו זה.
נגיד, הדלמוס, אני מסתכל על הדלמוס, כי הבטה ורז'ן לקורטקס, ואז כאילו בסוף לא היה מקום לדלמוס, צריכים משהו אחר, פשוט תוסיפו אקסטנשן מסביב, כי הדלמוס גם מקבל את כל הסנסור אינפורמיישן ועושה מולטי סנסורי קומפיוטיישן. כן, מה? לא יודע בכלל מה זה הקצת. אני בכלל לא מבין למה צריך גם קלאסרום וגם לאירואן. נכון? תלמוס זה סבבה, הוא לא... תלמוס, ההבדל בין תלמוס...
גילינו משהו יותר טוב על מה, למחוק?
ההבדל בין תלמוס ללאירואן זה שתלמוס קיבל את המידע לפני קורטקס, ולאירואן הוא בקורטקס. נכון, תלמוס כאילו חד משמעית קיבל את המידע לפני קורטקס, ולאירואן בגלל כאילו צמודים לקורטקס, הם גוסים על כל הקורטקס, הם מחברים אזורים שונים, למה זה את שניהם? בדיוק, זה מה שאני אומר, שזה נורא מבלבל, כי יש מצב שיש לנו תוספתנים במוח שפשוט מבלבלים אותנו לגמרי, כמו הבייזל גנגליה, שזה הרמה של תוספתן, שלוקה במחלות כל הזמן.
אז זה בדיוק העניין, כמו שתוספתן הדבר היחיד שהוא יכול לעשות זה להתפוצץ כאילו ולגרום למחלות, זה הדבר היחיד שהוא עושה. כן. יש חיים שכמעט יכולים להתקלקל.
כן, בדיוק,
אבל האנשים האלה שקשה להם לזה.
וואי,
כן, כי יש כשהוא מתקלקל אז זה כואב לך, אבל כשהוא תגיד, בסדר.
קשה לך, אבל גם כשאתה עושה את הדיפרנט סימולנטי, קשה לך, זה פחות אוטומטי הדברים. אז זה כן לדברים אוטומטיים, פחות תחשוב עליהם. כל העניין של הקפסיטי, של כמה דברים של זיכרון עבודה, שיש דברים שאת צריכה, נגיד אז הקורטקס, אם את עושה את כל הפעילות המוטורית בלי הבאזל גנגליה, אז את יכולה לחשוב על זה כאילו זה עושה רק עם הקורטקס, אז יש לך מוגבלת, לא יכולה גם לנהוג וגם לדבר, נגיד. אבל כל הקטע זה עם מה שטוב אמר, זה כאילו, הוא דיבר על זה שיש גיין קונטרול, נכון? למה זה לא יכול להיכנס לספרים?
גם אין עכשיו, זה
חשוב עוד משהו, שעושה גיין קונטרול, מה המודל שלי הוא חשוב כדי לעשות את הפרדיקשן עליו?
אני חושבת שכאילו המודל הוא יכול לעשות מערכות, ויש כאילו איזשהו מנגנון על, כאילו זה לא שזה המנגנון, שזה לעשות את זה. יש מנגנון
כאילו שזה יפותח לזוגות, זה לא נלמד, וזה לא רק נלמד. כאילו הרצון שלנו לאכול.
כן. נראה לי שבדיוק. אז מנגנון הוא לא הרי... מה? יש זה... מנגנון מסייע להם.
יש לנו מעגלים שהם אבולוציוניים, כמו הפחד שלנו מהכבישים לעומת גידחים. יש דברים שמתמודדים
הקומנט שלך...
אני עברתי למחשב ששמתי, היה לי במייל. אני עכשיו... איזה בין לקחת? סמרפילד זה המשפחות האלה. לא, זה יותר אהבתי. זה טוב, זה עם האקספרימנט.
כן.
רגע.
איך זה נהיה קומן של חיים? זה מעניין, אוקיי?
רגע, לא.
הם לא
את המיקרופון, איפה זה נמצא?
כן, אז הנה הוא על הסוף, הוא היה ברור על זה.
אוקיי, מוסיף.
Okay, we have our next comment.
Okay, I will present the comment about that will show some experimental results about this model, about validating or invalidating. Okay, first I would like to thank Chaim Tompolinsky. I understand this is something that we need to do in the beginning of every talk, so I'm going with everyone. Okay, so I for some reason I decided that much of the talk will include quotes from the article. It's not an article, it's a comment. So I will read the abstract. Okay, this is a positive, somewhat positive comment regarding the article. Clark makes a convincing case for the merits of conceptualizing brains as hierarchical prediction machines. This perspective has potential to provide an elegant and powerful general theory of brain function, but it will ultimately stand or fall with evidence from basic neuroscience research. Here, we characterize the status quo of the evidence and highlight important avenues for future investigation. So these are the two main things I will talk about in the comment. The comment is largely about that. So this is the first experimental result that Merav showed us last time that supports this type of model. So we have the task is this. So subjects are looking here. After several times we have, this is exactly what Merav explained. Subjects are seeing a square. If the square is green, it means very likely to have a face in the next image. If the square is yellow, then it's 50-50. And if the square is blue, then it's not likely to have a face. And then either a face or a house or an inverted face, doesn't matter, was presented to the subjects. The areas that they looked at were these, the fusiform areas, and the responses are as predicted by the model. This was also something. So if we expect a face, the face area will not be as active relative to if we don't expect a face and we see a face. This is because of the prediction error of this model. There's some problem with the mouse, sorry. On the other hand, if we see a house, the prediction error is high. When we expect a face, the prediction error is high, and the activity will be high. This is a supporting, yes?
So how much the activity is really related to error?
Actually, this is not a exactly the clear assumption. So, because you need to maintain the representation in order to make the predictions for lower level, and also you have some other areas, some other neurons that are either more or less active, and they are less active if the prediction error is smaller, and more active if the prediction error is larger. So this is not entirely built. This is not entirely fitting, but you can think of. Well, I did not see this graph here, but if the prediction error is the larger amount here, then this is what you would expect. So it's a little bit of a trade-off. But I agree with what you're saying, and it's important to keep this notice, and this will be one of the key things for later experiments. They will discuss this later. So another experiment subjects were shown the images on the random and the images in the 3D. You see the 3D images are consistent of about local features as the random images, of about the same local features, but they form together some kind of a shape. and the random images don't form any kind of a shape. So when we visualize the high-level representation, when we visualize the activation areas of the brain in high levels of representation and low levels of representation, so V1 and some LOC, we can see that if we subtract the activation of the subject to the 3D shape minus the random shape, we can see something like this. Okay, so like this means that the V1 areas, when the low-level characteristics of the shape were predictable from the higher-level understanding of the shape, then the V1 area is somewhat suppressed. And on the contrary, in the LOC area, so this is a higher... What?
No, it seems to me like the difference could be not just 3D versus random, but rather continuous versus non-continuous, or edges versus non-like.
Oh, so the control is not... Okay, so... okay, this is a valid point as well. No, I think it's very legitimate and even maybe true. But we are trying to. We are trying to understand or to seek out things that are somewhat supportive of this type of model. So here exactly we see what Yair asked earlier. So that the lower level of representation is suppressed. So this is due to the prediction error. So V1 doesn't translate any more information to higher level because it is well predicted by the higher level activation. But on the other hand, the higher level activations, they need to maintain some sort of a stable representation in order to make the predictions onto V1. So this is another sort of, I would say, positive experimental result. And this is another fMRI result. And now we will move on to, this is an experiment done in monkeys now, and it was extracellular recordings in some high-level visual area. And what we see, the experiment was the following. We have the leading images here and the trailing images. The leading images were always after the leading images during the training session, always after the leading image. This trailing image appeared, always. And this happened 816 times during the training session. Here, after this leading image, always this trailing image appeared, and you can see this for all these 6 images. And during the test period, you have this chukiyut, this regularity maintained, but not completely. You are measuring. What we wanted to do is in the test phase, we want to measure the response to this of neurons, and also response to things like this. After A1, to present B2. This was never presented before. This is something that is not predicted according to previous training data to the monkey, and it would be interesting to see what is happening. And we can see here that the result. This is the results to the regularities, to the things that are regular. There are neurons who are responsive to the first image, and when they are responsive to the first image, the second image is completely predicted, and there is no really. This is the average of several times, of the 8 times. So, but on the other hand, when you present something else, some other image that is not A1, and then you show B1, then it is novel, and you see this prediction error. I'm sorry, this is not prediction error. This is okay. So for the predicted case, you see a lot more suppressed activation to the same image. Okay, so this is here we are controlling the the same inputs to the system and with a different prediction. Either we have the prediction or we don't have the prediction. So we can see that when we have the prediction, the activity is suppressed. This is the blue. And when we don't have the prediction, the activity is heightened. So this is single neurons in monkeys. As you can see, this is the population response of all the neurons, and these are single neurons, specific neurons. And you can see this is also equivalent to what we would expect from the model. So another experimental result that is somewhat reminiscent of the model. There is one more result that I did not discuss, that was talked about in the comment, that was less clear, I think, so I took the liberty not to look at it. So this is a quote from the authors. You can see that at the macroscopic level, what I showed you with fMRI studies, he claims that they are modest but promising lines of empirical support for predictive coding. So there aren't many experiments done, but they are promising and there is something. And if we look at the microscopic and the cellular level, perhaps more importantly, as you can see, the data is scarce. So I think only two studies that he talked about, but also some promising data. So interesting. Looking to the future. So now what are the most important things to check in the future for the future experiments? The simultaneous prediction and surprise of a single processing stage. Okay, this is again what Yair's question was about. So we need to somehow balance or think how to measure at the same area both the prediction error, two distinct groups of neurons, both the prediction error neurons, the neurons that project to higher levels, and the neurons that project to the lower levels that need to maintain a consistent representation. This is an important thing to keep in mind. And also, we need to talk about hierarchical interaction with two different states. So instead of talking about two different distinct groups of neurons in one stage, we need to pay attention to the communication between two different stages. And this is the last quote. We hope that over coming years, neuroscientists will be inspired to collect this data. And I would like to thank Chaim once again, because this is what you do at the end of every talk. And that's it. There is no response I did not add the response by Clark because it was, yes, I agree with everything.
To me, none of those experimental results were surprising. In other words, of course, surprise responses exist. Any form of mismatch negativity or there are surprise responses all over.
But what do you mean? Of course they exist. This is an experimental result. On those kinds of results, these models were built.
Right, but what I'm saying is it's already been well known for a long time that surprise responses exist in the brain in sensory areas. What Clark is saying, what predictive coding maximalists are saying, is that it's not just that surprise responses exist, it's that the entire purpose of the feed-forward information is to generate a prediction error which is mapped to an internal model. And the fact that you can find surprise responses in sensory areas doesn't mean that that's all that the brain is doing or even if that's the main thing in the brain. It just means it exists.
Okay, first of all, I think the surprise responses are something that if you think of a brain as something that tries to take sensory information, for example, and convert it into a space where to represent it in an efficient way, in a way that it's easy to understand things, it's easy to know what is the proper action from this representation, you would not necessarily expect to see these surprising results. And I think this is the most widely accepted model or view of how our brain works. It is it's some kind of a representation machine. So you represent. You always you make the state of the world in a very compact and clean some neuron activation, and then you act upon them because it's very easy to act upon a very simple representation.
I understand that's what the theory says. I'm saying these experimental results don't really show that that is what the brain is doing. Because you have to go back to the theory in order to say these are representations of the theory as opposed to saying these are just, when you have the neurons that show surprise response.
Okay, so what I only said was that if you view the brain as this kind of a representation machine, that you wouldn't expect to see these kinds of results. Maybe you would, but in some other elaborate model, or it doesn't have to be that elaborate. In some other model, you might expect to see these results. And of course, this is only things that support this claim, but they don't negate all other claims, not even close. And I think you can think of. They highlighted the things they think are important. For example, the simultaneous prediction and surprise in the single processing stage, and hierarchical interaction with adjacent stages. But if you will not be convinced by that, I guess you can come up with an interesting experiment.
I think we mentioned it last time that for imaging studies, I think it's very non-trivial to come up with a resolution that has specific, that is in line with the specific predictions as opposed to a general notion of being actively making inferences about the world that have some coding of surprise. To what extent are we expecting to have any kind of response when we're not supposed to be surprised at all, at least within whatever, second and third, whatever, superficial layers, for instance, these neurons are expected to be, there is some, I don't know, often people that do monkey studies cannot really tell at what layer they are. I don't know, it seems people can say something, but there is something more specific to the prediction. Maybe optimally that there's no response at all, but you also have a specific prediction as to where within the it's going to be layers 2 and 3. Again, I'm not sure.
The mouse study, they looked at calcium imaging at layers 2, 3, and they found some neurons who are look like prediction error, and this is in line. I did not show. There is another reference in the comment about another paper that talked specifically about that.
In the imaging data, I agree with you, and the only thing that they found, it will take us how is it immediate to transfer between the two computers?
I think, yes, you just have to plug in.
So because, okay, just a second. Because for instance, going back to Summerfield, what do I do?
You want the...
First I want a picture. So I wanted to give just another study of Summerfield. One point. No. It's funny. פה. טוב, שנייה, just the things right. Okay, yeah, this is just one slide of Summerfield that I wanted to show that is in line with your question in a way. I talked about it, but I didn't show it last time, so this is another study of Summerfield, and Summerfield does imaging. So in imaging, you have a problem. How do you, what is your expected average result, given that you cannot have the resolution that they are expecting? So here is the experiment. It's the same kind of experiment. They show a series of, let's say, faces, and they have 3 types. The task is presumably is aimed to keep you busy and to keep you attentive to the stimuli, but is not really directly related to what they're actually asking, because they have to do something. There's, let's say, detect an inverted face. But there are 3, let's say, for our purpose, 2 types of blocks, right? One where you see repetition between adjacent stimuli, right, the same stimulus. So given the very, very well documented phenomenon of repetition suppression, which can be easily explained as an adaptation phenomenon, okay, there are many neurons, you have some averaging of their response, and in the second presentation of the same thing, they will respond less, and overall you get a smaller response. So this is a typical account for response suppression, but what they want to say is that response suppression is not just adaptation, there is a violation of prediction. So here they have another block where each trial is an alternation trial, where given that this is the phase presented on the first stimulus, the second phase will be a different phase. Okay, so it's well predicted that if you have one phase, the second phase will alternate, right? So you have a full prediction that this will not be repeated, right? And the question is, given that you fully predict an alternation, do you get an elevation of response when there is a repetition that violates your prediction, right? So it's kind of trying to negate adaptation, versus your ability to predict. And everybody predicts, everybody has a clear prediction. And this is actually a summary of their responses. So repetition trial. So this is a repetition trial, okay? So this is the magnitude, let's say the magnitude of a response of a repetition trial in empty bars, and non-repetition trial in the filled bars. The question is, can you have a larger response for the repetition when it's unexpected, right? When it's unpredicted? And the answer is no. This was a trick question. You actually have to look at the experimental results, okay? This is the alternating block, right? This is the alternating block. There is a response to the repeated trial within the alternating block, meaning it is the surprising trial, right? It's alternating, but here it's a surprising but repeated, right? Where is the larger response? But you're right, okay? It doesn't constitute a larger response. But, okay, when you compare it, the repetition, to the response to repetition, when it's expected, it is a larger response, okay? So there is some effect, right? There is some effect in the sense that when it's unpredicted, there's somewhat, let's assume it's a significant, you cannot tell from this graph, but let's assume it's significant. There is probably it is significant given that it's in the paper. There is an elevation of the response, but not to the extent that it really is the dominant response, right? So the thing is, the reason I'm putting it is because even when there is evidence, it's complicated. There is some evidence that we have elevated response when we are surprised compared to when we are not surprised, but the dominant, I think that the dominant part is that you do not manage to make it higher than the repetition part. Again, you can say, well, we're averaging across all sorts of things, but I agree with you. There's some evidence for surprise, but the very specific evidence is mostly still lacking. On the other hand, it wasn't really typically looked for, at least at the level of single neurons. It's very complicated. It's not obvious how to materialize it in a way to very, very specific predictions. So predictions are scarce. Last comment. Okay. סליחה.
Yeah, I did not know that it will be consecutive and what will be the first and the I don't have חוויות yet. Yes, I'm sorry. So I will now present, I don't know if it's working, I think it is. I will now present another comment. This comment sounded very interesting to me from the abstract, but eventually it was very, I don't know, I didn't like it. And I did not feel it was very coherent, and this Lars Mukli guy actually just referred to all of these papers during this comment, which is okay, but it also felt incoherent, and so I'm a little bit apologizing for that. So first, fine. Okay. So again, I will read the abstract. This is what enticed me. So also, Klaus offers a powerful description. Notice the same wording. The powerful description of the brain as a prediction machine, which offers progress on two distinct levels. First, an abstract conceptual level. It provides a unifying framework for perception, action, and cognition, including subdivisions such as attention, expectation, and imagination. So this is a little bit of burden of mine. Second, the hierarchical prediction offers progress on a concrete descriptive level for testing and constraining conceptual elements and mechanisms of predictive coding models. So this is actually a little bit related to what we talked in the end. So I'll talk about it when we get there. So the abstract level description. So understanding the brain as a prediction machine offers quite new ways to look at things. Okay, so it's also in the high level thought of it, in the abstract way of thinking about it. It's also when you disregard any specific implementation, it ascribes function to neuronal processes. Okay, so it has a meaning for the components. They have different meaning. So this allows us to think a little bit about two new things that usually and historically are a little bit less considered or less emphasized in the literature. And here I would like to remind everyone Shaul Hochstein's comment regarding Hubel and Wiesel, that what he told us that Hubel and Wiesel, in his opinion, did very groundbreaking work, but they took the field of neuroscience several decades backwards because of their disregard of this feedback that is going on and their representational thinking. Now I will describe what the authors mean when they say internal cortical communication, and they suggest some way to test these kinds of things. And after that, they will present an experiment that the brain processes. That is regarding the second thing. Okay, so they have a starting point suggestion to about how to test or maybe test or see things that are relating only and that are disregarding the input level and how that you cancel out the input and only look at the feedback connection using imaging studies. So first of all, excitatory projections from the LGN are a small amount of what drives what drives V1. So this is the first thing that drives V1, but most of what drives V1 are other cortical regions, and these are many. This is an illustration of many types of cortical regions that project to V1. So what are these things doing? This is an interesting question, and they suggest a way where you can look. So let's assume we have this neuron, that this is the receptive field or area around from in V1. Okay, so this is this is location in the image. This is the receptive area where it is responding, and this is also the input it receives from the LGN. And let's look at this also area in V1. So this area does not receive input from these LGN neurons. It only receives input from a different LGN neurons right here. So if we present visual stimuli here, we will have feed-forward connections only here, and feedback connections that will feed back a lot larger area of V1. So in this case, what it suggests that if we look at this X here, we are able to see, in response to a stimulus, we are able to see feedback results without seeing any feed-forward input at this X area. And they actually don't really do anything with that. They just suggest this as an initial way to start probing this feedback connections. And this is a paper from 2003, so it's a current opinions paper. 2013, I'm sorry. So this is a current opinions paper also, so more of a suggestion. Okay, so another thing they say that this conceptual framework is helping us to think about is what the brain does before we present any stimulus. So here they talk about other work they have done, which this Vetter paper, this was Vetter is a student of Mukli, or Mukli. Okay, so I will describe what they say about the paper, but not the paper itself, because it felt incoherent and I couldn't really follow it. We have shown that motion predictions are carried over to new retinal positions after saccadic eye movements, which confirm that saccadic updating incorporates predictions generated during pre-saccadic perception. Okay, so here they look at a single saccade as a type of experiment that a person is doing, and is generating in its own mind a prediction about what will be the result after the input result after the saccade. So this is very interesting, but what they showed was actually no data that I could decipher or I could understand really clearly. So, but they say that this type of thinking allows us, this type of predictive thinking allows us to think about saccade in this way. For example, that we want to make a prediction about what we will see at a specific location in space immediately after we move the eye to that location. Also, they say that this is a new paper that is under revision, that they have managed to change. So a TMS is a way to a little bit alter the activity in some brain region from outside the brain, and they say that when they